All right. A lot of molecules that we've seen so far, in fact, all the ones that we've basically dealt with, have been ones that have obeyed the octet rule. Okay? The general rule that elements typically end up with 8 electrons. That's the point at which we fill a valence shell. If we tried to add more, they'd have to go into another energy level. That would be much further away from the nucleus. More electron shielding's not really going to happen. There's not enough protons to attract them in a new energy level. But there are ways that we can violate the octet rule. Okay? There are ways that elements can have more than 8 electrons, and there are a few elements that will have less than 8 electrons. We already know, of course, about hydrogen and the duet rule for that first energy level where it's filled with 2 electrons. But there are other situations, particularly as we've come to know, as we go further down the periodic table, the rules become more like guidelines. So, as we go further down the periodic table, the octet rule becomes more like the octet guideline. And in fact, a lot of the elements will violate the octet rule by using d orbitals, by bringing d orbitals into bonding. Now, one of the reasons that those things are important is because there are a number of systems, number of molecules, where using those d orbitals is really important for getting a specific color. In fact, a lot of colorful compounds, a lot of molecules that we use as dyes have systems that involve expanded octets or exceptions to the octet rule. Okay, so we really need to understand how this is going to work. What kind of elements can violate the octet rule? What do they look like? How do we deal with Lewis structures when this has to happen? And so the basic rule is that elements in the second period, the second row on the periodic table, with the exception of boron and beryllium, will follow the octet rule. So elements in the second period with the exception of boron. Boron is so small, has so few protons, that it typically only forms compounds with 6 electrons. So boron is an exception because it'll have fewer. But our core compounds made of carbon, nitrogen, oxygen, and fluorine, those guys, the rest of the elements in the second period, those are going to obey the octet rule. Okay, in just about every situation, and certainly every situation that we're going to have to deal with. However, once we get down to the third period and lower, so elements like, in particular, phosphorus and sulfur are two where we see a lot of examples where they will have what we call an expanded octet. By using d orbitals as part of their bonding set, they can have more than 8 electrons. Those d orbitals are fairly close in energy. Those 3 ds are fairly close in energy to the 3 p's. They can, when the atoms combine, there's some funky stuff that happens with the orbitals that can allow them to be used to form chemical bonds. We'll talk a little bit more about that towards the end of this unit. So, a sort of prototypical example here is phosphorus pentachloride, PCl5. If we go through and do the system, right, phosphorus has 5 valence electrons. Our chlorine is going to have 7 valence electrons. But we have 5 of them. So altogether that gives us 35 from the chlorines. We have a total of 40 electrons to play around with. And hopefully by now you're starting to get into the flow of this process. We've counted up all the valence electrons, put our central atom in, put the 5 chlorines around, and we'll start with single bonds. Okay, a single bond for each of the chlorines. How many electrons did I just use up? Yep, 10, 2, 4, 6, 8, 10. Remember, each line, each bond represents 2 electrons being shared between the phosphorus and the chlorine. So how many electrons does the phosphorus have around it right now? 10. So that violates the octet rule. You can go 10, you can even go up to 12. That's about the limit, okay? 10 or 12 electrons around an atom. So phosphorus here is violating the octet rule. It has 10 electrons around it, but that's okay. Okay? Phosphorus can do that. Things in the third period and lower, our big examples are typically phosphorus and sulfur, where we see this happening. So we used up 10 electrons. We've got 30 left. Each chlorine needs how many electrons to fulfill the octet rule? Each one needs 6 more, and there's 5 of them. That's going to be 30. Sorry, that was a mistake. So we've got a structure here. When we're doing this with our Lewis structures, in general, we're going to take, if we have to violate the octet rule, we're going to do it with the central atom, where practicable. Okay? So, central atom, if it's in the third period or lower, can violate the octet rule. It doesn't have to. You might look for a way to do it without violating the octet rule first. And then you can go ahead and violate the octet rule if you need to. And there's also some stuff we'll talk about in a few minutes about, well, sometimes we can come up with a structure that does violate the octet rule, and sometimes we'll have one that doesn't and one that does. How can we tell what's really going on? Is there a way that we can theoretically predict? The real proof of all this stuff is to go in and make measurements. You can measure the bond strength. You can measure, in many ways, how these things are hooked together. And that is really the real sort of proof for what's happening. And sometimes the theory doesn't match the experimental results. Experimental results are going to win, and we need to adjust the theory to take into account those sorts of new results. Excuse me. So, exceptions to the octet rule. Elements in the third period and lower, particularly phosphorus and sulfur are big examples, can violate the octet rule. Boron frequently only has 6 electrons around it just because of its low atomic number. It just doesn't have enough protons to hold that many electrons, to hold 8 electrons around it. Okay? So, next twist on all this stuff. Sometimes when we go in and we make experimental measurements, we get some odd results and we need to come up with some way to explain them. Okay? One of the cases where we see this is the polyatomic ion nitrate. You can go through, you can do a Lewis structure for nitrate. You end up needing 1 double bonded oxygen. Remember, all these guys are going to obey the octet rule. But the question we ask ourselves is, well, I can draw the double bond on this oxygen, or I could draw it on that oxygen, or I could draw it on this oxygen. Which one is it? Can I tell them apart? Well, if I go into the lab and make some measurements, I should see one of the oxygen-nitrogen bonds much shorter than the other ones. Double bonds are stronger. The stronger the bond, the shorter it is. More charge in between the 2 atoms pulls the 2 nuclei closer together. So double bonds are shorter than single. Triple bonds are shorter than double bonds. The stronger the bond, the harder it is to break apart, the shorter the bond length. So we frequently use bond length as a, indicator of bond strength. So we go in the lab and we do these measurements. We'd expect to see 2 bonds that are the same, single bond length, and 1 bond that is shorter, double bond length. But if we go in the lab, what actually happens is we measure 1, 2, 3 bonds all exactly the same. And we measure all 3 bonds as shorter than a single bond, but longer than a double bond. It's in between. So, for Lewis structures, the way that we can modify this system, this theory, right, about what's going on, we need to modify our model in order to take into account this new experimental results, this new experimental evidence. So we can't say it's any one of these systems. We say that it is a mixture, a resonance of all three. Originally, you might think, well, what happens is the double bond moves around. But that's really not a great picture or not a great model for what's happening. It turns out that our concept of localizing the electrons, of saying, hey, I know that there are 2 electrons right here, doesn't fit very well with our quantum mechanic ideas about how we describe orbitals, which is all based on probability. So, Lewis structures, which are a localized electron model, that depend on saying we know exactly where the electrons are. One way to sort of combine this result with this localized model is to say, hey, these extra electrons are spread around all of the bonds. That none of these bonds is a single bond and none of them is a double bond. They're all a bond and 1/3 in strength. That they're spread around. And we do that with Lewis structures by drawing the 3 possible resonances, the 3 possible structures, and putting these double-ended arrows. Another way, a more modern way to notate that, is to actually do something like this, where we'll put a strong regular single bond and then these dotted lines here to indicate that we have a resonance structure. Okay? Don't worry about the positives and negatives on here. They're what we call formal charge, and something we'll talk about in a sec. But we use these dotted lines to indicate these partial bonds, these resonance structures. And then an even more modern model actually represents the electrons in the molecule as a set of orbitals, okay, what we call molecular orbitals, and shows the electron density of this system where there's some additional density due to the delocalized, the set of electrons that are actually spread around all the bonds. So for those delocalized electrons, we don't say, oh, here's where they are. We say, hey, the probability of finding them is spread around all of these bonds evenly. So you need to think about resonance structures when you have a set of models, a set of Lewis structures, where the only difference is, can I move the double bond around to the different atoms? So here I had 3 oxygens and a nitrogen. This double bond can be on each of the different oxygens. In doing that, I can't distinguish between all 3 of these, and in fact, that double bond is spread around all the bonds. It's delocalized. You can't do that. Because of the way that bonds form, at most you can have 1 triple bond or 2 double bonds on any single atom because of the way they form. You can have lots of single bonds, but because of the way the bonds form, which we will talk about, you can't do that many double bonds. You can only have 2 double bonds at most on any atom. Okay? All right. We're sort of opening up a can of worms here in terms of lots of different structures that we'll be able to draw. And that sometimes now there's going to be several different ways that we can come up with a structure. Does it follow the octet rule? Does it not follow the octet rule? Are we using resonance? Are we not using resonance? We need a way to sort of keep track of all this stuff and try and have a system that's going to tell us what's the most likely structure, what's likely our best structure. To do that, we use something called formal charge. Okay, we use something called formal charge. So formal charge is essentially a way of doing a little bit of electron bookkeeping. And what it tells us is how much is an atom in a molecule deviating from its normal state. The more deviation from its normal state, typically the worse that structure is likely to be. This is just a theory. It's not, you really have to go in and make measurements to validate, to really know what's going on. But formal charge works fairly well to help us be a little bit more accurate in our predictions. So, for instance, the sulfate ion. Okay, sulfate ion. You can go through and you can do a Lewis structure for the sulfate ion that follows the octet rule. So this Lewis structure for the sulfate ion follows the octet rule. You can see the sulfur has 8 electrons. Each oxygen has 8 electrons. This follows the octet rule. It is also, however, possible for me to come up with a structure where the sulfur violates the octet rule. Okay? We would like to know, is there some way that we can determine whether the follow the octet rule or the violate the octet rule is a better structure, is more likely to be what really happens? So to do that, we're going to look at each atom and we're going to count up how many electrons do I have assigned to that atom in my structure versus how many valence electrons does it normally have. To do this formal charge counting, each bond counts as 1 electron for each atom. It's like we're splitting it back apart. Okay? So, normally oxygen has how many valence electrons? Normally oxygen has 6 valence electrons. In this system, we have given the oxygen, we've assigned the oxygen 7 electrons. 1, 2, 3, 4, 5, 6, 7. The bond counts as 1. Okay, like you split the bond in half, 1 electron to the oxygen, 1 electron to the sulfur. So we take the number of valence electrons it would normally have, and we subtract the number of electrons we've assigned, and that tells us the formal charge. This oxygen has a formal charge of -1. All the oxygens have a formal charge of -1 because they're all exactly the same. 6 lone electrons or 6 lone pair electrons, 1 electron from the bond. Now we look at the sulfur. How many valence electrons does sulfur normally have? It normally has 6. How many electrons have we assigned to the sulfur in this structure? 4. 1 for each bond. So 6 minus 4 gives the sulfur a +2 formal charge. This is good because if I sum the formal charge all together, it should add up to the charge on the molecule. The charge on this molecule is -2. The sum of the formal charge is going to be -2. And in fact, in this other system, the sum of the formal charge will be the same thing. It's going to sum to -2. What we're interested in is which structure has the lowest total amount of formal charge. In other words, I have 4 negatives and 2 positives. I know that I have to end up with at least 2 negatives. That has to be. So I'm looking for a structure that minimizes the total amount of formal charge. If you look at absolute values, this has a formal charge of 6. I'm looking for a formal charge lower than that to tell me whether this structure is better than this one. In this structure, we have 2 different oxygen atoms. That's the change we made. We used some of these lone pair electrons to form additional bonds. This oxygen on the top is still the same. It's got normally 6 valence electrons. We've assigned 7 to it. It's exactly the same as this one. It has a formal charge of -1. Versus these double bonded oxygens, they have 6 valence electrons like all oxygens do. But now they only have 1, 2, 3, 4, 5, 6 electrons. So this oxygen has a formal charge of 0. Okay? This oxygen has a formal charge of 0. So I've got -1s here, okay, and 0 on this one and this one. The sulfur now has gone to 0 as well. Again, sulfur has 6 valence electrons, and now we have 1, 2, 3, 4, 5, 6 assigned to it for our formal charge. So the total formal charge on this molecule is -2, which of course it has to be. It has to match the charge on the molecule. But the absolute value is 2 as well. So this structure is better. And in fact, It's better still because it's actually this formal charge on each of these oxygens is actually spread around all four, because I can draw a resonance structure for this molecule. I can draw a resonance structure where the double bonds could be resonating across all the oxygens. So each oxygen really has a formal charge of -1/2. Take-home message for this: lower formal charge is better. Not the sum of the formal charge, maybe the sum of the absolute value. But the lower the formal charge, in general, the better the structure is. This is particularly important for elements that can violate the octet rule. Frequently with elements that can violate the octet rule, you can draw a structure that follows the octet rule, and you can draw one that doesn't. If you check the formal charge, the one that doesn't follow the octet rule will frequently have lower formal charge, indicating a better structure, a more stable structure. Okay? All right. The dyes, with their resonance structures and their delocalized electrons, typically those are important features of those kinds of things, what we call conjugate systems. And we won't talk about that a whole lot, but we will talk a little bit about it in the lab we're going to do next week. These sort of delocalized electrons very frequently can make energy jumps in the visible range more easily than individual atoms. And so those dyes tend to be very colorful. But to bond these things onto fabrics, we have to start to talk about a whole other property of the molecules that has a lot to do with the electronegativity and the polarity we talked about at the very beginning. So we need to start to think about not just individual bond polarities, we need to start to think about a molecule as a whole. So we need to add a couple more pieces to our understanding of these molecules. And that's what we're going to do for the next couple of days. We're going to start to look at their actual shapes. We're going to look at how those shapes combine with the electronegativity differences to tell us whether the molecule as a whole is polar or not. And then we're going to go ahead and say, hey, how does this all fit together? How can we explain all this stuff? All right?